The story of the day happened in 1666 when Newton started his private studies. Rumor has it that Newton sat below an oak tree. Here you go, our little Newton. All in a sudden, an apple fell and hit Newton's head. Newton asked the following question: what will happen if you throw the apple forward? Just imagine if you throw the apple forward with a certain small velocity, v. Well, then you know what exactly will happen, right here. If your velocity is sufficiently small, you got something like a projectile. And then, well, Newton imagine, what if you throw your apple a little bit harder? And your classmate will tell me, well, I know that Mr. Chang, that will move a little bit farther. Still a projectile accelerating under uniform acceleration g. But then, if you throw it sufficiently hard, wow, then the apple can do something magical. It can turn around the earth and hitting Newton's back. So the topic of the day, we are going to talk about the green case, and we name the motion of the apple right here uniform circular motion. To fully understand what's meant by uniform circular motion, first of all, we have to define some new terms for this motion. Now, let's refer to the circle right here. Suppose an object travels from B to C as I illustrated, and the angle involved right here, theta, and the time taken, t. So right now, we are going to define a new velocity. Traditionally, you have the old velocity, the velocity from our chapter 2 of your textbook. V equal s over t. Well, this is what we call linear velocity. And now we would like to have something new. We would like to have something specifically designed for a circle, and we call that angular velocity. Well, as you can see from the word here, angular, that refers to angle. Angular v, and angular v that is similar to linear v in a sense. It's not displacement over time, but angular displacement over time. We'll denote the angular velocity with the Latin symbol omega. Example. Well, the Earth will complete 1 revolution in a day. So what is the angular velocity of the Earth? The answer is pretty straightforward. Well, in a day, the Earth rotates 360 degrees. But, well, students should note that in circular motion, we will not make use of our 360 degree, but instead we will say it's a 2 pi, and this is called radian system. And, well, all in all, 2 pi radian, that is 360 degree, and later on we'll see the advantage of that. And so right now the angular velocity of the Earth should be omega equals 2 pi over 24 times 60 times 60. Students should note that the unit for angular velocity is radian per second. Another example. A minute arm of a clock moves 360 degrees after 1 minute. So what is the period and angular velocity of this minute arm? The definition of minute here is similar to that of wave. So period t, that's straightforward. And now the angular velocity omega. Well, since the arm rotates 360 degrees, and that is 2 pi from the radian perspective. So that is 2 pi over 60. And once again, our unit radian per second. Well, now student, you may have noticed one very important property of angular velocity, angular velocity and period t are interrelated and is governed by omega equals 2 pi over t. Another quick practice. How large is the angular displacement of the minute arm in 20 minutes? And we should express our answer in radian. Bear in mind 360 degree is identical to 2 pi, which means theta is 2 pi, and 20 minutes, that should be 1/3 of a whole revolution, so 20 over 60. And therefore your answer should be 2 pi over 3 radian. Let's do a little bit more complicated example. Well, now suppose I got a Ferris wheel turn roughly 2 cycles in 1 hour, and each cabin is 150 meters away from the center of the wheel. So here we got 2 questions. First question, what is the angular speed of the Ferris wheel? And the second question, what is the linear speed of each cabin? For part A, similar to previous example, omega, that is 2 pi, and note that you have 2 cycles in 1 hour. So 2 pi times 2, that is 2 cycles, and 1 hour, that is 3600 seconds. And therefore, you have your final answer. And just bear in mind the unit radian per second. For part B, you have to recall a bit of math. Bear in mind in junior form when we want to calculate arc length. Well, the formula for arc length, that is arc length equals 2 pi r times theta over 360. And note that in our system here, 360 is 2 pi. In radian system, if 360 is equal to 2 pi, that means you have arc length 2 pi r times theta over 2 pi. And now you can see that you can eliminate 2 pi. And once you eliminate 2 pi, you have a surprisingly simple formula for arc length. And arc length is equal to r theta. Now let's imagine, how do I calculate our linear velocity based on our angular velocity? Well, note that the original definition of linear velocity, angular velocity, as we have talked about that is theta over t, and linear velocity, that is displacement over time. And displacement right here, that's roughly equals to our arc length, which is r theta over t. And once you observe this expression very carefully, well, let me adjust my position a little bit. Once you observe this equation a little bit carefully, you see theta over t, that is exactly our angular velocity omega. So now we have an expression to relate v to omega, and that is v equals r omega. And refer back to our question. If we ask about what is the linear speed of the Ferris wheel, and given you have omega 3.49 times 10 to the power negative 3 by v equals to r omega, that is 150 times 3.49 times 10 to the power negative 3, and for linear speed unit, meter per second. I guess this is pretty much for today's material. Now work on your follow-up examples based on the worksheet distributed, and we'll continue in the next video.